Welcome back. This is an Aleks training video on relating activation energy to reaction rate. Activation energy is the energy that you have to put into something in order to get a reaction to occur. It's heating something or putting something at higher concentration or something like that in order to make it happen. Once it happens, you may get energy back if it's exothermic. Something might get hot. Or you may make a reaction happen that's endothermic, where heat energy has to be stolen from the environment. Either case, you're still going to have some kind of an original investment of energy in order to make a reaction happen. Okay, reactions rarely happen automatically. They normally need a little bit of a incentive or a little bit of push, and that's the activation energy. So the activation energy is higher than the beginning. Okay, and it acts like a hill in between where you are and where you're going. So they're going to give you an example here of two reactants that are coming together to form two different products. Okay, and so they're going to give you some information about it. So A plus B equals C. Okay, that's the first one where your C is products, A and B are reactants, and your second one is A plus B equals D. D is the different products, A and B is the reactants. Okay, so for instance, oxygen and hydrogen can form water, or oxygen and hydrogen can form peroxide. Okay, it's the same thing. You could make more than one thing. And whenever you make something in a chemistry lab, many times you're going to have more than one product. You're going to have the one you want, and then the one you don't want. And if you're a drug company, you may have to throw away lots of the product that you don't want to sell because it was the stuff you didn't want that it made. Okay, so here's an example like that where you're making C and you're also making D. But they're different reactions. They're happening in the same test tube at the same time, but they're actually different chemical stuff going on to do it. So here's your information. Reaction 1 is endothermic. Reaction 2 is exothermic. All right. What does endothermic mean? Let me just draw a sketch. By the way, you're just asked to draw a sketch here. It doesn't have to be anything specific where you have to know numbers or anything. It's just a relationship. So let's say I have my reactants here at some energy level. Okay, so energy would be going up here like this. So this is some energy level, and then it's endothermic. That means the products are going to have more energy than the reactants. Okay, so this is endothermic. More energy in the products, less energy in the reactants. Well, if there were no activation energy, it would simply go from the lower to the higher. It would simply go from low to high. And activation energy is going to be a barrier that you have to cross that's usually higher than both of them, both the products and the reactants. So you would have some kind of a barrier like this, okay, whatever that would look like. And your activation energy would go from the level of where you start to the top. This would be the energy of activation, E sub A, or activation energy. This is your products or reactants. So this is A plus B, and here's your product C, and that's endothermic. The opposite would be exothermic. You're going to start at that same level. Okay, so here's A plus B, and you're going to be exothermic. That means your thermic or your heat energy is going to leave. Well, if it left, it means it was there to start with. It was stored in the bonds of the reactants, and now the bonds of the products don't need that much energy. Okay, so the remaining energy leaves. That's exothermic. Okay, so this would be exothermic, and the activation energy is that barrier between the first and the second. Okay, and your activation energy here is lower because you're not going from the bottom, you're going from your reactants up to the top of that. So this would be E sub A, and this would be D. Okay, so A sub B to D. Now, let's see if it makes sense. It says if the reaction vessel is charged or filled with A and B, then at first D is produced faster than C. You can see why D would be faster than C. Let's imagine that we're throwing snowballs. Okay, here's me and my friends, my buddies over here. We've got snowballs, and here's our enemies on this side. We would have to throw snowballs over this entire distance in order to slam our enemies on this side. That's harder because I have to act against gravity. I have to act against higher energy in order to make the snowballs go. Okay, here, if I'm up on a ledge and my enemies are down here, to throw snowballs here would be easy. I have a short wall to cover that, but then it would easier land. So making D faster than C makes perfect sense energy wise, because the energy it takes to overcome this barrier from this side to this side is very low. To go from here to here is higher, and so it's less likely to make C than D. You're going to be more likely to make D than make C. Okay, so that's an energy diagram and rate, because it would make D faster because there's less energy required to do it. So more of these have a chance to have the energy required to go to the other side. Fewer of these would have the chance of energy. Like if you were simply just making popcorn and you were making it, the popcorn would splash out of the bowl. If you have if you have a very high walled popper, the chances of popcorn coming out are low. If you have a very low walled popper, the chance of popcorn coming out are higher. It's the same. The reaction rate is tied to the activation energy. So I think they're asking is to make a couple drawings. You'll make a drawing like this, you'll make a drawing like this, and then make sure that this is A, B, and C and A, B, and D. All right.